There we go. Welcome, everybody. A special welcome to Professor Bart Kahr from NYU. It's a pleasure to have him. Well, of course, it would have been nice to have him live here, but maybe next time. It's a pleasure to have him here at our colloquium today. Just a little bit of an introduction. He did his postdoc at Yale, and then he moved to Purdue as an assistant professor, and then at the University of Washington as associate professor, and then in 2009 at NYU as professor of chemistry at the Molecular Design Institute, where he is still at the moment. He works on crystal growth mechanisms, polycrystalline pattern formation, interactions of light with organized medium. And today he is gonna explain to us why are crystals straight. So without further ado, Bart, please, the floor is yours.
Thank you so much, Laura. It's a pleasure to be here. And I appreciate the fact that everybody showed up. I know it takes a little bit of extra discipline in the age of Zoom, and I really appreciate that. And I'd like to share with you this morning my developing misunderstanding about what crystals are. I thought I had sorted that out long ago, but it's becoming ever fuzzier, and that's sort of delightful, actually. Now, a few years ago, I had a great pleasure and privilege of going to see the biggest crystals in the world. They are in a cave in Chihuahua, Mexico. These are crystals of gypsum that are 20 meters long. And this is like the a natural cathedral sitting underground. And if these were the only crystals that you knew about, what would you know about crystals? And you would know that crystals are straight, they are polyhedra, they're bounded by sharp edges and flat faces. And that's kind of how we understand what crystals are. And that's part of the reason why crystals have been so attractive, not only to scientists, but to human beings generally speaking. In fact, recent research has shown that very early humans, hominids, used to collect quartz crystals for no good reason. They weren't used as tools, they weren't, had no function, but they were different. They were different from everything else in nature by the virtue of the features, the geometric features that they have that we find so attractive. So you have a set of basis vectors, semi-infinite translational symmetry, you get a lattice of points, and this naturally leads to terminations as polyhedra. And this was all well and good until I stumbled across a book called Gedrillte Kristalle, which literally means drilled crystals, but the drilled part is in quotation marks. And I think the author meant a couple of things by this word. He meant like a drill or twisted, helicoidal, and he also meant rhythmic, like a military drill in which you have soldiers marching all in phase. And I think those are the two things that he was trying to evoke with this word: crystals that are twisted and crystals that are growing with some kind of rhythm. And this is an extremely rare book. There's only 3 copies of it in universities around the world, and my personal copy is the 4th one that I know about. And there's more complete Gutenberg Bibles in Germany, for instance, than there are copies of this strange little book. And I was captivated by the title, but more so, I was captivated by something that the author said inside that I thought was really crazy. And I was really motivated to study this book only so that I could have the opportunity to write one funny paper about how a crazy old guy thought that most crystals were not polyhedra, but in fact they were twisted. This fellow Ferdinand Bernauer, the author, reported that about 1/4 of crystals made out of molecules can twist as they grow. And these are simple kind of off-the-shelf organic molecules like benzamide or aspirin, as is in the second case, that are growing as needles, but they're clearly twisting as they are growing. Now, in most of the crystals described in this book, the helicoids are not isolatable as individual crystalline objects, but rather the helicoids grow as radial ensembles called spherulites. And the telltale signature of the optical twisting is the rhythmic procession of the refractivity along the radii. And so these bands tell us that something is growing as needles radially, but as the crystals grow, they twist so that you're kind of looking at the threads of an optical screw from the side. And the differences in the interference colors speak very directly to this twisting. Aspirin was one of the examples in Bernauer's book, but in order to really impress upon modern scientists that this was a super common phenomenon, we got a hold of the 3 other common over-the-counter painkillers and showed that indeed all of them can be made to grow with this characteristic optical rhythm. And that's how common this is. We had a lot of these in the laboratory. I think that that was a sign of the times rather than anything else, but something we might want to examine why we had so many legal painkillers in the laboratory, let alone illegal ones I don't know about. In any case, this was what Bernauer's book was about. And, I tell my students, okay, you can have prejudices in science, you just can't publish them. We had to go check it out. And it turns out that this crazy old guy was right. But in fact, if scientists had been mindful, generalization of the morphology of molecular crystals could have gone back much further still. For example, here's young Pasteur, who is famous for establishing a correlation between shapes of crystals, macroscopic chirality, and microscopic chirality, the actions of individual molecules dissolved in a solution and their effect on polarized light. And this was his famous work with the salts of the tartrates. But Pasteur was he was an ambitious young guy, and so he wanted some more papers. And so he thought, oh, whatever I did with tartaric acid, perhaps I can do it with malic acid. And he describes growing both racemic and optically active malic acid and characterizing them by taking their melting points. These are the right substances that we know today. And he describes taking his melting points kind of in the old-fashioned way that students do it in organic chemistry laboratory. You put a little bit in a tube next to a thermometer. But if he had melted them on a hot stage and looked in a microscope, this is what he would have seen. And Pasteur was a darn good optical crystallographer. And if he had looked at his melted malic acid, he would have unquestionably realized that his crystals were helicoidal. But nobody had invented a hot stage for the optical microscope in Pasteur's time. It came about a generation later. And we're confronted with the mystery of the so-called hemihedral facets in Pasteur's tartrate. What is it about the molecular structure that causes the expression of that dissymmetry in the polyhedral crystal? But here's a crystal of benzimide. It doesn't only have one hemihedral mirror reflectionless face, but every surface is in essence a hemihedral surface. And Pasteur could have known that if he was looking for it. So I hope I've convinced you that this is an old, a very general thing that is not so well appreciated today. And what we wanted to do after we were convinced that it was a common thing is to explain the why of it. Why do crystals twist? And the first question you might ask is, well, if you take a crystalline rod and you twist it, how much energy does that cost? And if you did twist it, where did the forces come from during the process of growth? And so the elastic energy to twist a crystal is a Hooke's law type of expression. It's quadratic in the twist angle. And it depends upon the fourth power of the radius approximately. And so that's why it's easy to twist a nylon thread, but to twist a steel beam is ever so much harder. But for crystals that we measured their dimensions for aspirin, it turns out that the energy required to twist a mole of this material, given the dimensions of the individual lamellae that we observed, is very small, just 6 joules per mole. I'm a chemist, so I don't understand any units of energy unless it's energy per mole of something. So we converted it to mole, and it doesn't take a lot of energy, which we were pleased to discover, because if it required lots of energy, it's not really, we weren't really sure how it could possibly be a common thing. But that didn't really answer the question of why. Where do the forces come from? And with my colleague Alex Stukenberg, for a long period of time, we wrestled with the why of it. And we had some ideas and mechanisms, and we tested them, and we had discovered some interesting things. But we didn't find a satisfactory universal answer or mechanism. And then just a few years ago, we started to think about it differently. What if we're asking the wrong question? What if the real question is not why are crystals twisted, but why are crystals straight? Let's flip the question over. And once we did that, it was more or less not so much pushing a boulder up a hill, but it was like following one rolling down a hill. A lot of pieces started falling into place when we asked the question in a counterintuitive way. And we got some real assistance in our new understanding from a mathematician, Effie Efrati at the Weizmann Institute. Now here's my formula that I showed you, this Hooke's law formula for the twisting of an elastic rod. Effie is in the physics department at the Weizmann Institute, but he's really a geometer first and foremost. He's a mathematician by training. And he had a completely different way of expressing the elastic energy of a twisted crystal. And this is Effie's formula. And I show you this formula in order to emphasize the fact that mathematicians are different from everybody else. And oftentimes they're not very helpful because they are so different. But the beauty of having Effie as a collaborator is he always translates his analyses into experimental mathematics that anybody can understand. And so this is what he did. He took helicoids and he cast them out of silicone rubber. And the helicoids had some characteristic pitch as cast, T0. And then he asked the question, what happens to the pitch if I take 4 of these and glue them together? Now, in order to glue helicoids together, you have to straighten them out, untwist them, apply glue on one face, and then press them together. And when he did that, he saw that in these tetrads, the pitch was expelled as the square of the radius. And then he took 4 of these tetrads and made a 16mer. And again, the pitch is expelled as the square of the radius. Now, at the same time, my student Chao Li was trying to evaluate this twisting process in silico for a molecule benzyl. And you can grow big straight crystals of big polyhedral straight crystals of benzyl. Some people call this the organic quartz because it has the same shape and the same symmetry as quartz. But you can grow microcrystals that are helicoidal. What Chao did, though, is she made a crystal in the computer from the CIF file. She made a hexagonal rod, 6 by 6 by 30 unit cells, and then she allowed this rod to relax under the constraints of a force field. And you can see that it goes from a straight configuration to a ground state that is clearly twisted. And we observed that as we made these calculations for thicker and thicker crystals, the pitch is expelled as the square of the radius. That is, atomistic models under the constraints of force fields and molecular dynamics behaved in exactly the same way as Effie's rubber and glue. And these experiments led us to the following hypothesis that arises in the ubiquity, the commonness of twisting. And that is that some crystalline nuclei may acquire translational symmetry only because they cannot continue to take advantage of the thermodynamic driving force of growth unless they straighten out. So the idea, we don't see very clearly the crystal nuclei of 1,000 molecules, say. And because we don't see them clearly, we have assumed that they are just like big crystals, only smaller. In kind of the same way that, in the Middle Ages, for example, they didn't seem to know how to paint children. They just painted them as little miniature adults. It's not really clear why in the Middle Ages children didn't look different than other people, but that's how they did it. And likewise, we don't really see crystalline nuclei very clearly, so we think that probably they're just like regular crystals. But in fact, translational symmetry is something that some crystals earn, and they earn it at the expense of the intrinsic frustration that molecules invariably have because there are big restrictions on macroscopic crystals. So for instance, a crystal can have 1, 2, 3, 4, 6-fold rotational symmetry, nothing more, nothing less, unless they want to abandon the idea of a regular lattice and adopt a quasi-periodic lattice. But molecules can do whatever they want, of course, right? Why wouldn't molecules like to make a 5-1 screw axis? There are some molecules that surely would like to do this. But if they want to be in a crystal, they are not allowed. And so they have to choose to regularize themselves to a symmetry that's consistent with long-range translation if they want to continue to grow. If they want to continue to take advantage of the crystallographic thermodynamic driving force of growth, they have to straighten out. They have to behave. They have to conform to society's rules. Otherwise, they can stay twisted and just be nanoscopic twisted objects. And there are legions of these kinds of things in chemistry, but they're size limited. They don't get beyond the nanoscale. And they don't get beyond the nanoscale, we believe now, because growth does not provide enough energy for them to untwist in order to continue to grow. And obviously, if you have something that is intrinsically helicoidal, if it were to grow radially but maintain its pitch, then it would have to keep getting crazier and crazier and crazier with each subsequent generation. Many things in chemistry are twisted and nanoscopic just because they cannot figure out how to straighten out. And many things in chemistry are straight, not because they want to be or because it's an axiom of crystallography, but rather because they couldn't continue to get large unless they straightened out. Bernauer said about 25% of simple molecular crystals, when small, can adopt a twisted configuration, and our decade of studying this has caused us to slightly revise his statistics upward. But more recently, we have turned our attention to a different class of molecular crystals, those molecular crystals that possibly have electronic applications, like organic semiconductors. Of course, we have to get somebody to sponsor this research. And so we thought we would start focusing on crystals that had a function. So things like twisted monocomponent organic semiconductors do this very regularly. And even more common are the simple organic charge transfer salts of electron-rich donors and electron-poor acceptor molecules. And you can just mix donors and acceptors and make these colorful salts, and you can make 100 of them, in a semester. And from the statistics of mixing and matching donors and acceptors, more than half of them can be made to grow with a twisted configuration, which is an extraordinary thing to say in 2021, since these compounds have been studied intensively since 1970s and sort of have created the subject of molecular material science. So some cynical person once asked Michael Faraday, what's electricity good for? And he said, famously, of what use is a newborn baby? And so because we have to get the grants and so on, we asked, of what use is a twisted crystal? And so we framed this experiment. Let's take a crystal and let's hook it up to an external potential. And then we can measure the charge mobility if it's a semiconductor. And then let's take the same crystal but twisted, hook it up to an external potential, and measure the charge mobility. Which is a better conductor? Is it twisted more conductive, less conductive? And more importantly, how would you even think about something like this? So we want to make this comparison. And the plan is to do it on field effect transistors, to lay down twisted crystals and their straight isomorphs across the gap of a organic field effect transistor and measure the current. Now, throughout my career, I've spent much more time and energy chasing photons in crystals than electrons in crystals. But I have a wonderful colleague, Professor Stephanie Lee, who is at the Stevens Institute, or was at the Stevens Institute of Technology, which is just across the river in New Jersey. And Steph is an expert on the electronic properties of organic crystals. So we framed this question and we pitched it to the National Science Foundation, and we were lucky to be supported. And then, of course, came the health crisis. And it's nothing, we couldn't do anything with our new fortune. All we could do was think. And so turns out that I had a brand new PhD student, Young-Fun Yang, and since she was a brand new student, I didn't really know if she was a good thinker. But I asked her, how would you think about this while we were all sitting at home? And it turns out that Yangfan is a really good thinker. And this is what she thought. So first I'm going to show you how Yangfan calculated the charge transport in a straight crystal. And then I'll show you what she did in order to make a comparison for crystals that are twisted. I want to emphasize that, there's nothing here in quantum chemistry that we invented. We're just pushing other people's buttons, but we're pushing other people's buttons in application to a new kind of a problem. So the first thing you have to do is calculate the intrinsic quantum mechanical coupling of molecules. This is the so-called transfer integral. And you have to make this calculation for pairs of molecules that are at different orientations with respect to one another, but close. This is a compound that we got from Yves Hertz in Brussels. And it's a nice compound because temperature can be used to control the pitch. So you can see this big pitch at 50 degrees and a smaller pitch at 40 degrees, and then essentially straight crystals at 65 degrees. Next thing you have to do is calculate the reorganization energy, which is the geometric relaxation that occurs on the charge transfer surface. And for this, you need the ionization potential and the electron affinity. And then once you have the transfer integrals and you have the reorganization energy, then you can use Marcus-Husch theory in order to calculate the hopping rate in different directions. But because we have anisotropic objects, the hopping is going to have an angular dependence. That is, the carrier mobility is a second-rank tensor, which relates the current density to the applied direct electric field, which may not be in the same direction. And in this way, these are results for 3 salts of tetracyanoethylene, a very strong electron acceptor. And these are 3 polyaromatic hydrocarbon donors, phenanthrene, pyrene, and perylene. She calculated the angular dependence for hole and electron mobilities. So all this is for a straight crystal. Here I have a straight crystal on the left. But now we have to do it all over again, but we have to compare it to a crystal that is twisted. And so Yangfan transformed the coordinates with twists of 1/100th of a degree between adjacent layers in the crystal. And the 1/100th of a degree comes from the fact that the pitch, the repeat in the band spacing is about 10 micrometers. And if you consider the thickness of layers to be about 1 nanometer, that turns out, the thickness of layers to be about 4 angstroms, that turns out to be about 1/100th of a degree per layer. That's how this was configured. And then we have to do all the 4 steps over again, but with one more additional step. Because if you twist the thing, it's no longer a single crystal. And so the molecules further from the twisting axis have been displaced more than the molecules that are close to the twisting axis. And so what we had to do, I thought I had another picture, but then what we had to do is average the transfer integrals over this whole area. And Yangfan took 25 selected points in order to make a sampling. And in this way, she got some numbers and predicted that twisting is helpful for charge mobility by a factor of 1 to 2. And for a property like conductivity that has such a great dynamic range, this is not really, it's not something that's going to change any industries. But nevertheless, it was very important to be able to have a systematic way of thinking about what might happen. And now, just in the last few months, we've now had some more action on the streets, and we have been able to go back into the lab, and Young Fun has been able to do the experiment. She's been able to measure for this compound the mobility as a function of the pitch. And in fact, both for electrons and for holes, the mobility increases with the decreasing pitch. It's better for holes if the helicoids are running across the gap of the field effect transistor, and it's better for electrons if they're running in parallel with the gap for a field effect transistor. That's what we basically established. It's sort of consistent with the calculations that twisting is better than straight for some reason, both by computation and by experiment. However, there's a disconnect, a substantial disconnect between the calculations that we made and the things that we measured in the laboratory. Because the calculations were made on individual twisted fibrils, but the measurements were made on innumerable fibrils that were tightly packed together. So it's a little bit of an apples and oranges comparison. And what we really need to do is to find organic semiconductor crystals that grow as individual isolatable helicoids. And that's harder than finding banded spherulites with lots of needles packed together. But then I was at a Zoom meeting not too long ago, and I was looking at the posters, and you might ask, does anybody really look at the posters at Zoom meetings? And I can assure you that some people do, so don't lose heart. And I saw a poster by Lizzie Kilaleo, who works in the Nottingham group of David Amabilino, and she had this poster. This was and I thought, my goodness, she stole my SEMs, or I stole her SEMs, or somebody stole something. But actually, there was no shenanigans going on. This is just a really common phenomenon. And this compound, it ought not be a great organic semiconductor, but it might be something that we could measure the mobility in. And so then the task for us was to get a conductive AFM, one in which you can use the probe to make an electrical conduct with the sample. We can grow these crystals, just as Lizzie says, as individual helicoids. Here's an AFM, and we just have to get them from an ordinary AFM onto a conducting AFM. I mentioned Stephanie, it turns out that during the public health crisis, we had a hiring freeze, as did most universities, and nothing was happening. But by some miracle or set of miracles, we decided to send Stephanie a rowboat and to have her relocate her laboratories right next to my laboratories. And so she became a faculty member at NYU. And when you get a new faculty position, sometimes they give you some money. And so she just unpacked a brand new asylum conducting AFM. And so we're moments away from being able to do the experiment on individual helicoids. That's really great. Except for the fact that, Laura, Stephanie is now occupying your office, the office that you have when you visit Stefano. But the one closest to me is still vacant. So if you would not mind moving down the hall just a little bit. We're still in good shape, and we welcome you to come back. Now, Laura said I was the penultimate speaker, and so that's important because these are just the penultimate acknowledgements. I want to conclude with real acknowledgements by telling you a little more about this guy, Ferdinand Bernauer, to whom we owe a big debt for having distracted us from our normal business with a very unusual book and proposition. And I thought I'd just tell you a little bit about this scientist and perhaps why his book never really caught on. He was trained as a mineralogist in Heidelberg, and he was conscripted during the First World War to dig trenches. And so he was digging trenches in the Lorraine Valley. Now, digging trenches, you know, doesn't seem like a great job, but if you're a mineralogist, you can get some work done. And so his very first scientific paper was about phosphorite minerals in Deutsch Lothringen in 1919. He doesn't seem to, he's not ready or willing to concede the Lorraine Valley to France at this point in 1919. And this was work that he did from his work during the First World War, digging trenches. But his ankle was destroyed during the war. And so when he got back to the university in Berlin in Charlottenburg, what used to be the predecessor of the Technical University in Berlin, he just retreated to looking at things in the petrographic microscope. And it was in this way that he ultimately, accidentally, I think, discovered the kind of ubiquity of twisting in molecular crystals in all of the organic compounds that he could get from colleagues in Charlottenburg and elsewhere throughout Germany. Now, he studied with a guy called Solomon Calvi in Heidelberg. This was his PhD mentor. And Solomon Calvi was distinguished by being the local champion of Alfred Wegener's theory of continental drift. Everybody thought Wegener was crazy. They thought he was crazier than I thought Ferdinand Bernauer was crazy. But Solomon Calvi was Wegener's supporter in the notion that all of the continents were joined up at one time. But then in 1933, the National Socialists came to power. Solomon Calvi was of Jewish descent, and so he moved to Turkey, where he founded the geosciences department at the University of Ankara and helped develop a water system for Ataturk. And it's curious that it was in 1933 that Bernauer re-engaged with his training in field geoscience. I don't know if his leg got better or if he was motivated by the misfortune of his mentor. But in any case, in 1933, that was the year that Bernauer started going back into the field. And he first started studying sulfurous volcanoes. And one of the first papers that he wrote appeared in a very funny journal called The Gas Mask. And the papers, it basically says, if you're going to be studying sulfurous volcanoes, bring a gas mask. Now, it's funny that there is such a journal like this, but there was an entire generation of men who used gas masks and built gas masks and were really interested in gas masks. And under those circumstances, maybe not such an unusual place to publish a paper. And he's continued studying volcanology, and eventually, he did something that is remembered for the ages, not his volume on twisted crystals, but for a trip he made to Iceland, in which he measured in real time the separating North American plate and the Eurasian plate. And this paper is captured in a landmark book of the foundational papers that established the theory of plate tectonics and continental drift. And so this is a scientific contribution that will have him remembered for generations. In 1945, he was in Berlin and he was hit by a bomb from the Royal Air Force. And so, that perhaps is part of the reason why his ideas and his book didn't have the longevity as I think the content deserved of them. But in any case, this is, I just leave you with a photograph of mannitol, in which you have a spherulite, a banded spherulite growing in the melt at bottom, which meets an air interface. And when it meets the interface with air, you can see the individual springs flying apart from one another, almost like the coils in an old mattress. And so we thank Bernauer for his stimulating work, and we thank you for your attention. I'm happy to answer any questions.
Thank you very much, Bart, for the very nice talk. The floor is open for questions. As always, you can either unmute yourself and ask the question or write it in the chat, as you prefer. No, I have a couple of questions I can ask.
I have a question.
Okay, there you go. Please,
thanks for a very interesting talk. I really enjoyed it, Bart, the wider context later on you gave at the end. Well, I'm mostly making amorphous coatings via ALD, so I know a little about crystals, but I was just wondering, you explained that these twisted crystals that you're just starting to understand why they form. The formation of needle-like structures versus more compact cubic-like crystals, is that something that's already much more explained in literature, or is that also still topic of investigation?
No, that's kind of easy to explain from linear elasticity theory. And so when crystals are fibrous, they have a small cross section, and the elastic energy for twisting has a shape constant in it, and the shape constant is goes as 1 over the inverse 4th power of the radius. And so it just becomes much harder to deform things that are thick than things that are thin, and that perfectly agrees with our common experience. And so it's not absolutely true that only fibrous crystals twist, but the great majority of them have extreme aspect ratios. And the trick for getting crystals to grow like this is to get them to grow under the highest crystallographic driving force that you can, in order to allow growth to happen very far from equilibrium. Now, it's hard to get things to be very far from equilibrium without just spontaneously nucleating and ruining all your fun. And so the trick is to get them to grow far from equilibrium, but to not nucleate like crazy. And when you're very far from equilibrium, you tend to get extreme aspect ratios. That is, the crystals only care about where they're going to get their next meal. And their next meal in a melt is radially, just growing outward. And that it kind of explains the round structures made out of thin fibrils.
Okay, thanks.
Yep.
Can I connect to the question? Basically that means that you can create crystals that are straight and they're twisted from the same material.
Yes.
Okay, because
Yes,
I was like, how are you
changing
measuring?
the growth
Okay.
conditions. Yes, and
Okay.
we can actually grow twisted crystals, and then we can watch them untwist as they get fatter. So imagine
Oh,
you
that's
have
cool.
so imagine you have a crystal that's very thin, it's a needle, it's twisted, and now it starts packing on more molecules on its sides. As it packs more molecules on its sides, it's creating new elastic stresses that want to drive the crystal back into a straight configuration. And so you can actually watch them expelling the twist as they get fatter. And
Wow,
so,
that's super cool.
yeah. So we've seen with our eyes, I mean, the story I told you today, we've seen movies of it with our eyes.
Wow.
I have that confidence in what nonsense I'm saying.
I have a question.
Yes, please, Alina, go ahead.
Yeah, so this is just out of curiosity. Can you tune your twist by maybe like tuning the temperature of the crystallization, or how do you tune the twist?
Yeah, so temperature is the most easily controllable parameter especially from melts, because we don't have, we can't adjust the concentration. So temperature really is our best parameter. And if you lower the temperature, the twist gets tighter, generally speaking. We've also shown that you can decrease the pitch by shearing. So we have now a viscometer, and we're shearing the melts as they crystallize. And shearing, for some reason, also makes tighter helicoids. I don't know. In no case do we have a theory where temperature or viscosity is a parameter that we can plug in, and that some formula will tell us what the pitch is. We don't have such a theory yet, and the trouble is, like, temperature can affect a lot of things in different ways. It can affect the diffusivity, but it can also affect the driving force, and these things can go in opposite directions. And so, yeah, it would be nice if we could predict the pitch with some kind of a formula, and maybe someday.
Thank you.
I have a question as well.
Yeah, please go ahead.
Van der Heijden. Yeah. Thank you for a very nice presentation. I was wondering, if you look at the morphology of crystals, then you know that additives can determine the shape of these crystals. Play additives also a role in the twisting mechanism, and why?
So a huge role that I avoided mentioning for the sake of simplicity. So generations ago, microscopists used to fix their slides with the sap of the Canada balsam tree. So Canada balsam is a naturally occurring resin. It contains lots of terpenes, and it melts as a isotropic transparent glue. And this is how microscopists used to fix their cover slips to slides. And I think that Bernauer accidentally mixed some of his Canada balsam with the crystals that he was growing, and he saw this twisting, because while it's not required, Canada balsam and other resins like Damar gum, which artists use, and some others, can encourage the twisting process. And what we believe is happening here is that the resin, at about 10 weight percent, will increase the viscosity of the melt, decrease the rate of nucleation, and then allow you to get to larger undercoolings further from equilibrium. And of course, if you're looking for something interesting in science, you want to be as far from equilibrium as you can be. And so our aim is to get far from equilibrium, and additives, resins, help us do that. synthetic polymer, so we're looking now at mannitol, reduced sugar. There are two really good additives for making mannitol twist. One is the synthetic polymer polyvinyl pyrrolidone, which is a binder that, a synthetic polymer that is used as an excipient in lots of pharmaceuticals, a synthetic polymer. And the other really good additive is sorbitol, which is just a stereoisomer of mannitol. And so these two, things couldn't be more different, but they have remarkable effects. And we think that it has to do with the effect on the viscosity of the melt. And that's why we got a viscometer so that we could measure this kind of stuff. And that's how we discovered that shearing seems to turn crystals around themselves.
Okay, thank you. Thank you.
Are there more questions in the audience?
Can I ask one more?
Yes, please, Alina, go ahead.
Just wondering, have you taken a look at the mechanical properties of the twisted versus the untwisted? Like, for example, do the molecular interactions change due to that?
Yeah, so we would love to be able to measure the Young's modulus and the torque on twisting, and we would love to put these things through all of the mechanical tests that a textile scientist might investigate a fiber with. There's a general field of analysis called dynamic mechanical analysis, where they measure the viscoelastic properties of all kinds of things. And this is like, this is old-fashioned material science, but to us, it's, kind of outside of our experience. But we've just connected with a guy in our engineering school who is developing new kinds of dynamic mechanical analysis machines with the company Anton Parr, and has all kinds of sample chambers and sample mounting apparati that go along with it. And so it may be that he can help us with this kind of stuff, but we haven't gotten too far in that direction.
Well, thank you.
You're welcome.
Well, if there are no more questions, I think we can thank Bart again. Thank you very much for your talk.